In any complex system, whether it's a company or a government, there's always a push to solve problems and reduce risk. And, the most common way to do that is to create a new rule. But what happens when that same rational process is repeated over and over again?
Well, the assumption is pretty straightforward. If we add more rules, we get more control. And that should mean more safety and predictability. The reality, though, is often the exact opposite. As rules pile up, they can make a system more brittle, more fragile, and actually more likely to fail in unexpected ways. And that outcome reveals a really fundamental paradox in how we design systems.
So, to really deconstruct this, we'll first look at the paradox itself. Then, we'll define what we mean by a system and its parts. After that, we'll analyze the core logic that drives rule creation, see how those rules accumulate, understand how all of that leads to brittleness, and finally, uncover a more general law of diminishing returns that governs it all.
Let's start with this central puzzle. How is it that a series of decisions that all seem perfectly logical on their own, adding one rule to solve one specific problem, can end up creating a globally illogical outcome? A system that's less effective and even more vulnerable than before. You see, the paradox really begins with a flawed assumption about human behavior. System designers tend to believe that people will process every single new rule with the same amount of diligence. But our attention? It's a finite resource. As the sheer volume of rules grows, the ability of any one person to understand and apply them all correctly starts to break down.
Okay, so to really understand how this breakdown happens, we first have to examine the system in more abstract terms. This isn't about any one specific organization, but really about the underlying structure that's common to so many of these complex systems.
At its core, a system like this is designed for a purpose. It's meant to achieve a goal by making the actions of a lot of different people predictable and efficient. And the rules, well, they're the main tool we use to manage all the risks and uncertainties that come with operating in the real world.
So we can break this system down into 4 key components. First, you have the rules themselves, the procedures and the constraints. Then you have the actors. Those are the people who have to operate within the system. You have the designers, who are the ones creating and changing the rules. And finally, there's the environment, the external world that the system has to exist in. It's the interaction between these 4 parts that really drives how the system evolves.
Now, a system doesn't become this complex by accident. There's a core mechanism, a very powerful feedback loop that is constantly pushing it toward adding more and more rules.
And this loop is incredibly simple and compelling. First, a problem comes up, an error, an unexpected event. In response, a designer creates a new rule to stop that specific thing from happening again. And it works. The specific problem gets solved. But there's a side effect. The total number of rules has just gone up, which means the overall complexity of the entire system has increased.
This cycle gets reinforced by a cognitive bias that's pretty well documented. When we're faced with a problem, our default instinct is to add something. A new feature, a new process, a new rule. Subtracting or simplifying is just a less intuitive way to think, and so it's a much less common response. This bias makes the growth of complexity almost inevitable.
And here's the thing. Each new rule, when you look at it by itself, seems totally reasonable. It was created for a good reason. But the cumulative weight of all these additions creates this hidden burden that just keeps growing over time. This phenomenon has a name. It's called instruction creep. And because it happens incrementally, just one rule at a time, often to handle some minor edge case, it's very, very difficult for anyone inside the system to even notice the burden that's growing until it's already become overwhelming.
Let's visualize this. In the beginning, a simple process within the system can look like a straight line. The path for an actor to get from the start of a task to the finish is clear, it's direct, it's efficient.
But after years of instruction creep, that path has changed. New rules, all designed to handle exceptions and prevent errors, have added checkpoints, detours, and approval gates. The path is still there, but it's much longer and it's full of friction. It now takes more time and more energy just to get to the same goal.
And eventually, the system can reach what you might call peak complexity. The process is now a maze. That original, simple path is completely buried under a web of interconnected rules. It has become so convoluted that it's almost impossible for an actor to navigate it correctly, which leads to inefficiency and, ironically, whole new kinds of errors. This rising complexity doesn't just make the system inefficient, it makes it brittle. Failure stops being about individual mistakes and instead becomes an emergent property of the system's structure itself. So, you can visualize an actor's possible actions as a grid.
In a system that has very few rules, there are lots of open pathways. The actor has a high degree of latitude, which allows for flexibility and for adapting to changing conditions out in the environment.
But each new rule acts like a barrier. It blocks off one of the cells in that grid. As more and more rules are added, the number of available pathways starts to shrink. The actor's journey becomes much more constrained and a lot less direct.
As more rules pile up, that latitude for action continues to diminish, and eventually you might find that only one highly inefficient path is left. The actor is now forced through a rigid, inflexible procedure, with no room left for judgment or adaptation.
And then a tipping point is reached. With the addition of just one more rule, one more blocked cell, that very last path can be severed. The system enters a state of gridlock where no valid path forward exists. At this point, failure isn't the result of an actor's mistake. It's an outcome that was made inevitable by the very structure of the rules. This whole process, this creeping complexity and emergent gridlock, it isn't unique to one type of organization. It actually reveals a universal principle about the relationship between rules and a system's effectiveness. What you see is a law of diminishing returns on complexity. So, going from a state of low regulation to medium regulation, adding rules actually increases the system's effectiveness by creating necessary structure. But there is an optimal point. Beyond that peak, each new rule provides less benefit and adds more complexity, which then starts to reduce the overall effectiveness.
Now this raises a pretty obvious question. Why don't systems just remove the rules once they've passed that point of peak effectiveness? Well, the answer lies in a concept called active inertia. The very rules and processes that led to past success become deeply embedded in the organization's culture. They become these rigid commitments that are just very difficult to change, even when they're no longer working.
And this brings us to the final outcome. The very mechanisms that were rationally designed to solve problems, the rules, the procedures, the controls, they don't stay neutral. Through this slow, almost invisible process of accumulation, these very solutions gradually transform into the source of the system's next and often much larger problem.